Hey, so this is Joe, and this is the third video of Chapter 12 in Stewart's Calculus, and we're going to be talking about the cross product today. And so this is the other kind of vector multiplication that is new in this course, and it's a new operation that we do between vectors. And unlike the dot product, the cross product, the result of the cross product between two vectors is a vector. And so your book gives a formula for the cross product between two vectors and expresses it directly in vector notation like this, but it's a long formula and it's mixing the A's and the B's the components of A and B and the two numbers, and it's very confusing. But they also provide you a definition for the the cross product, sorry, using the determinant of a matrix. And now this is definitely the easier way to remember how to do cross products if you remember how to take the determinant of a 3x3 matrix. So the way we write out the cross product between two vectors, we write it out like this. We write vector A, the big X. Now this X we're no longer in fourth grade. This doesn't mean multiplied by. This means the cross product of vector A and vector B, and that is equal to the determinant of the matrix, the first row of which are all the standard basis vectors, I, J, and K. And then on the second row, we'll have the first vector in the cross product, so in this case it's A, and all of its components, so it's A1, A2, and A3, then all the components of the second vector being cross-producted, if you want to think about it like that. So we get B sub 1, B sub 2, and B sub 3. And we're taking the determinant of this matrix. So if you don't remember how to take determinants, it's not that you don't need to know how to take the determinant of any sized matrix for the sake of this course, but you do need to know how to take the determinant of a 3x3 matrix like this. So we can break this down, and so we isolate the I, and we look at the square that is kind of adjacent to it. So this square right here. And so we write out a 2x2 matrix, A2, A3, B2, B3, and it's the square that the point kind of touches. If you imagine these as all being squares, the point of this square touches the point of that little square right there. So we take the determinant of that matrix times I, then we subtract, and we imagine these two columns right here get fused together, and we take the determinant of that matrix. So we have this column A1 and B1, and then A3 and B3. And we take the determinant of that matrix, and those are both around the J component right there, so times J. And then plus, and it's important to note that minus right there, plus, and then this 2x2 matrix, the point of which touches K. And so that would be A1, B1, A2, B2. Take that determinant times K. And now, taking the determinant of a 2x2 matrix is very easy. We do this kind of cross thing. We multiply the two that are across from each other and subtract the product of these two across in like an X. So we'll get A2 times B3 minus A3 times B2. And then that is going to be times the I standard basis vector, and so minus, we get A1 times B3 minus A3 times B1 times the J standard basis vector, and then we get A1 times B2 minus A2 B1 times the K standard basis vector. And so now we have the vector written out in terms of I, J, and K. That means we can also easily write it out in bracket notation, taking the coefficients of I, J, and K. So this is the product of the cross product. This is what the cross product of two vectors is equal to. And as you see, it is a vector. And so this is the formula that your book could give you directly, but I recommend that just in order to not make mistakes in terms of memorizing this formula, to always start with the determinant and work from the determinant on. That is just my recommendation. But so that's kind of how we solve cross products algebraically and in terms of finding the cross product. But now, what does the cross product mean? Well, basically it has some very interesting graphical repercussions for us. So say we have we write out our three-dimensional axes right here. We have the x-axis there, the y-axis there, and the z-axis here. So we've got z, y, and x. So if we have any two vectors, we can call that A, we can call this B, B vector, then the cross product of A and B, and so we'll call this product vector the cross product between A and B, the cross product is going to be orthogonal to both of the vectors that are in that cross product. And we can call that binormal. So we'd say that the cross product of two vectors is binormal to those two vectors, or it's perpendicular to both A and B, or both the vectors that you use to make that cross product. And so that's interesting for a lot of reasons. First, if we map out our axes right here and the corresponding standard basis vectors, we got the I, J, and the K. And if you look at this, the K vector is perpendicular to both the I, the J vector, the J vector is perpendicular to I and K, and the I vector is perpendicular to both J and K. So we have this relationship where K is equal to the cross product between I and J. We've got I is equal to the cross product between K and J, and we've got that J is equal to the cross product between K and I. So a lot of very interesting graphical things come out of the cross product. But if you remember, and so we'll talk about that a little bit more later, and when we're doing some sample problems, and especially in the next chapter when we start talking about planes, because a plane, you have a normal vector to a plane, and that vector will be equal to the cross product between two other vectors that lie in the plane. But that's for the next chapter, just to kind of show you that there are interesting graphical things that we can get out of the cross product, whereas with the dot product, not many interesting graphical things we can do with it, more kind of conceptual ones. But so if you remember, we have our rule with the dot product. The dot product between A and B is going to be equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, right? Well, with the cross product, we've got this interesting property that that the magnitude of the cross product of A and B, and so the magnitude, that's important to remember, is equal to the magnitude of A times the magnitude of B times the sine of the angle in between them. And so that means that from the cross product, we can also figure out orthogonality and parallel, whether or not two vectors are parallel using the cross product. However, if you need to find out either of those two things and not a binormal relationship, I'd recommend that you use the dot product just because it's easier to solve. Because with this, you need to solve the cross product, which is a little bit of a lengthy process, then find the magnitude of it, which is also kind of an ordeal. But this is an interesting relationship nonetheless, and it proves useful in certain instances. So now we're going to talk about a couple of algebraic properties with cross products that are a little tricky and definitely a lot more tricky than some of the properties with dot products. So these are actually very important when you start doing proofs and things like this with vector operations. Alright, so we got our first property, which is probably the most important one, and that is that the cross product between A and B is equal to the cross product between negative B and A. So what this implies is that the order in which you take the cross product does in fact matter. This implies that the cross product between A and B is not equal to the cross product between B and A. And this is very important because it kind of prefigures what is going on with what all these other properties say. And basically it's variations of this, that the order in which you take the cross product matters. And that kind of makes sense considering that we have that rule that I talked about at the very beginning of the video, that when we take that determinant of that matrix for this cross product, it matters which the components of which vector go on top and which go on bottom. And it's the components of the first vector here that go in the middle, and then the components of the b vector, the second vector being cross-multiplied, cross-productified, that goes on the bottom of the matrix. So order does matter. However, nonetheless, when we've got property number 2 tells us that we do have a sort of distributive property with the cross product, that if we take the cross product between A and the sum of B and C, we can really make that the cross product between A and B plus the cross product between A and C. So it's a sort of distributive property. However, order does matter because you have to still, even when you distribute, the first vector here has to be multiplied first if A is first in this initial cross multiplication, as shown by property number 3, where if C is being cross multiplied second after the sum of 2 vectors, oh yeah, that is a vector right there, then C always has to be last when you distribute it. So that kind of makes sense because order does matter. Now number 4, there's not too much that I have to say with this property right here. It's just one to remember for doing proofs. Now number 5 is important. You take the cross product between A and another cross product of 2 vectors, and you can end up not having to use a cross product at all. You use the dot product and multiply it by a vector minus a dot product multiplied by a vector. So even though there are 2 dot products here, and you may say, oh, hey, that's weird. How can a cross product turn into dot products, and dot products are a scalar, not a vector? Well, that's because you're multiplying this scalar. It's really scalar multiplication. You're multiplying a scalar by a vector, and you're multiplying a scalar by a vector. So you still end up with a vector, just not one that you have to find using a cross product, which is sometimes really nice when you're doing proofs, just because cross products are a lot trickier to solve than dot products. So now, here are some actually pretty interesting geometric properties of cross products that I'm going to show you here in just a sec. So the first geometric property with cross products is the parallelogram property. And this is actually kind of a bizarre one, but it comes in handy when we're doing 2D vector algebra and vector geometry. And what this property says is if we have a vector, and it works in 3D as well. You can do this with 3D vectors also. But if we have some vector A and some vector B, and now this might start looking similar to our parallelogram rule with vector addition, but it's a little different. If we make a parallelogram out of this, so we have another A right here, same vector, and another B, this vector, and we make a parallelogram, when we take the magnitude, the cross product between A and B, and find that magnitude, that is going to equal the area of this parallelogram. That's a kind of weird property, and to be honest, I don't really understand the proof for it too well, but it's something that's very good to know, and will prove to be helpful when we do some geometric analyses using vectors. And now our second property is the parallelepiped property. I'm not going to write that out for risk of boring you. However, what it states is if we have three vectors, A, B, and C, and we make a parallelepiped out of them, so we have our A, we've got our B, and we've got our C coming out here, and we make our parallelepiped, so we got a B here, got a B there, we add another C up top here, we have another B right there, we've got another C here, and we've got an A here, we've got another C here, you can see where this is going, we've got an A, and then we've got a B back here, and we've got a C up there, or sorry, that's an A, and we've got an A up there, and we've got another A here. The volume of this, so the volume of that parallelepiped is going to be equal to the dot product between A and the cross product of B and C. And now this is always going to end up being a scalar, so I'm going to throw some absolute value here, value bars around here because the volume is always going to be positive, but that is an expression for the volume of this parallelepiped. And again, I don't really understand this proof, and it's nothing that's explained in your book, or the book that I used for that matter when I took this course a few years ago. However, this is a very interesting, of course, and useful property to use when doing geometric analyses using vectors. And now we have one more interesting property with vectors, and it's one that's tied in closely with physics, and it has to do with torque. Now, torque is the rotational parallel to force. You know, for those of you who haven't taken physics yet, if you are going to take physics, you're going to cover this a lot more in depth. But basically what torque does is torque is what allows something to gain rotational acceleration, in the same way that force is what makes something have a translational or linear acceleration. So they're very closely related. And what we have when we get torque is say we have a bar and it's attached by a hinge right here, some pivot point. And this bar has some length, and we're going to call that length r. Now let's say we apply a force at the end of the bar, some downwards force, and that force is a vector, and it's perpendicular to the bar, to the radius. This we can calculate the torque exerted on this pivot point by using this r and this f, this force and that radius. And when the radius is perpendicular to the force, torque, which is expressed by that symbol right here, so the amount of, and from there you'd be able to calculate how much angular acceleration this bar could end up having, that torque is just equal to the magnitude of the force times the magnitude of the radius. Now, there's a proof that we can get to for what I'm about to tell you, but already you know, what's an expression where we have the magnitude of two vectors multiplied by each other, and then an implied one? Well, either the dot product or the cross products have a formula like that attached to them, but which one of those would have this implied 1 when the angle in between the two values is 90 degrees? Well, when sine of 90 happens, that's equal to 1. So we can already kind of guess, maybe the cross product of these two gives us torque. And that's exactly right. Torque, generally described, is a vector that is the cross product between a force applied, did this backwards. The radius comes first, the cross product of the radius and the force. And that's our expression for torque. And so, graphically, this is very interesting, and I don't know if we cover this too much in physics, but torque can be thought of as a vector that pops out from two forces being applied, that pops either in or out of your paper when there are two forces like this, and that's kind of ties in with the right-hand rule when it comes to torque, and you'll learn more about that in physics. Basically, it just tells us when it's positive or negative. If you put your hand at the pivot point and curl with your palm along the radius and curl your fingers down towards the force vector, and if your thumb points up, the torque is positive, and if your thumb points down, the torque is negative, and that's our right-hand rule. And obviously, you have to be using your right hand for that to happen. So, since our torque is equal to the cross product between our radius and our force vector, then the magnitude of torque will be equal to the magnitude of our force times the magnitude of our radius times the sine of the angle in between them. And that's just a cool physics application of the cross product, and there are many more applications of the cross product that we could use, but these are the main ones that are taught in this course. So now we're going to do some practice problems. So we're going to do number 39 on page 839 in your book, and the problem says, so we have a bicycle pedal, and that's this pedal, and the crank arm is going to be our axle, or our radius, is pushed by a foot with a 60 Newton force as shown. And so the 60 Newton force is being applied to the crank arm at an angle of 70 degrees away from the pedal and 80 degrees away from the arm. And that arm is going to be our radius. That's going to be our R. So that R is 18 centimeters long. And so we need to find the torque about P, about this pivot point. So we have our two components that we need for figuring out torque. We've got our force vector, and then we've got our radius vector right here, and we have the angle in between them. So let's go over to the white screen, and we can solve this problem. So we've got our R, the magnitude of our R is going to be 18 centimeters, but since force and torque are both in terms of Newton meters, we are going to say that we're going to consider this 0.18 meters. Now, and then our force vector, the magnitude of that force vector is 60 newtons. And and the angle in between them, that theta, is 80 degrees. And we'll keep this in degrees for now, because eventually you'll be able to use your calculator. So we set up our equation here. We've got the magnitude of torque is going to be equal to the magnitude of the cross product between the radius and the force vectors, and since that's the magnitude, that's all we want. We want to find out the magnitude of the torque, not the direction. We've got the magnitude of the radius times the magnitude of the force vector times the sine of the angle in between them. So now we just start plugging in. We've got 0.18 times 60 newtons times the sine of 80, and you can plug all that into your calculator. Remember, that's 80 degrees, and you'll figure out the magnitude of the torque. So that's not too tough. You just kind of conceptually need to understand how torque relates to a radius and a force, and how to apply your cross product formulas. So now let's go do one more kind of sample cross product problem. Alright, so now we're going to do number 1 on page 838, and the question asks us to find the cross product between A and B, given that A is this three-dimensional vector and B is this three-dimensional vector. So once again, this isn't going to be a terribly heady problem. It's just kind of to get you used to doing cross products and feeling confident in doing them. So that is going to be equal to, we're going to set up our determinant. We're not going to jump straight to the formula just because this will kind of make sure or ward off some mistakes. So A is the first vector that's being cross productified, and so we put that in the middle right under the standard basis vectors. So we've got a 6, a 0, and a -2, its components like that. And then the B vector, we've got its components 0, 8, and 0. And now we can expand this out and do a couple matrices. We'll get 0, -2, 8, and 0 times I minus 6, -2, 0, and 0 for J, and then plus this last 2x2 matrix. We've got a 6, a 0, a 0, and an 8, and that is the coefficient of our K standard basis vector. So now we take these determinants. This is pretty easy. This will get us a 16 because a negative and a negative is a positive, and those two zeros, that ends up being 0. I minus, and then that's 6 times 0 is 0, minus and minus is a plus. That'll also be a 0, and this negative remains. So that will be minus. Yes, so this will be minus 0, essentially. And then this will be plus. We take the determinant here. That's going to be a 48, and then a 0, and so that is 48K. And so this 0, there's an implied J there, but it's all 0, so you don't need to write it out. So you'll get a 16I plus 48K, and we can write that out in bracket notation as well for you guys, and that'll be a 16, a 0, and a 48, and that is the cross product between A and B. So there you go. I hope that was helpful. Stay tuned for the rest of the videos. In this section, we'll just be doing more algebra and kind of picturing of vectors in three-dimensional space. So stay tuned.